Right, we've talked about data decomposition. Let's talk about functional decomposition. Data decomposition was pretty straightforward because what we were doing was taking, say, elements of a for loop um, and decomposing that somehow. And the example we used was that heat transfer example. And so we had elements assigned to core one and core zero and core two and core three, and we just managed to split up the work among the cores. Okay, functional decomposition is different. It's not data. You're not using the same equation on different parts of the data. Functional decomposition is, well, you've got different functions. And my favorite example of this is SimPark. And SimPark I thought was just a great game. My kids loved it. You put in plants and you put in animals, and the animals wandered around. And if the animals didn't have enough to eat, in our version of the game, we said, oh, the animals have wandered off to try and find more food. Yeah, okay, that works with small kids. But anyway, this is a perfect example because you could write a function that just does the tree simulation, the plant simulation. You could write another function that does the bear simulation and the deer simulation and so on. Okay, that's what functional decomposition means, is you're breaking it up by functions. But it's going to take some different organization to do that. And you have a functional decomposition project. So yeah, this is worth knowing. All right, so yes, we talked about SimPark. And again, there are pieces here that um, all have to play together. And that's really the important part. If the bears and the deer could just go off on their own, then you wouldn't need functional decomposition. They would just run. But the fact that each group has to interact with the other, the animals need the plants to stay alive. The amount that the animals eat the plants, that changes the amount of plants that are there. So yeah, and in Sim Park, you're also interacting with the climate and you're interacting with the money you're willing to throw into the park and all of that. So all these functions have to work together somehow. Okay, yeah. So um, really, what we're talking about is a current state, next state issue. Is we have now variables and they're going to look at the state across the entire simulation and then they're going to decide what happens to them next. So if the plant looks at the whole simulation and sees that there's a million deer out there, well, it knows that in the next step, it's going to be gone because the deer will eat them all, which means in the next step, the deer will be gone. So yes, each step, each function, each part of the simulation looks at the whole simulation state and says, what does this mean for me? And that's all that function has to do because there's other functions considering what does this mean for the bears? What does this mean for the berries? What does this mean for the bushes? And so on. So we have a now state and we have a next state. Now the trick is you need to synchronize these quantities, right? Is yes, they're all going to look at the state, but they're all going to compute their next state at different times. The scheduler is weird. We don't, or unpredictable, let's call it that. The scheduler is unpredictable. And so, yes, the bear may figure out their next state long before the deer do, just because of the scheduler. So there needs to be some sort of synchronization there, okay? Because they can't start writing out or values into the now array until they know everybody is done using the current now array. So we have to worry about that. So the synchronization will be accomplished with barriers of some sort. Quantity one knows what its now state is. It does its own computing, and now it's got its individual next state, and so on. But again, nobody can write out to the global state. Nobody can overwrite the global state until everybody is done using it. Okay, so it really sort of works like this. set up the now variables, calculate environmental parameters, spawn the threads using OpenMP sections. And this is a good use of sections because you know how many you have ahead of time. Otherwise, we could use tasks. And for each quantity is going to have its own process. Using the now state for the entire simulation, compute what its next variable state's going to be. Down here, copy the next state into the now state. But there has to be a barrier, and all the threads have to respect the same barrier because B over here is computing its next reaction from the now state. Okay. And in a simulation like this, you also have a thread, I call it the watcher thread. And really, it doesn't have to do much with the simulation, like nothing, but its job is to do things like print out the results, increment the time, calculate new environmental variables. What season is it? Is it hot? Is it cold? Is there rain? Is it dry? And then everyone goes back up to the top, something like this. Okay. So here we go. We're setting up the number of threads, and we've got 3 sections: animals, plants, and the watcher thread. Each one of the threads has the same structure, okay? A while loop, and typically this is like a time, like you're simulating for 10 years. So maybe you're doing 1 a week for 10 years. So while the week number is less than 520 or something like that. But you basically just stay in this loop over and over until you have a reason to quit. Maybe this is an infinite for loop because you quit when the user exits out of the program. Fine. Okay, so the watcher does nothing, but it has to wait at the same barrier. Watcher does nothing again, but it has to wait at this barrier. And now the watcher does, well, it writes out data into a file, it advances time, it recomputes temperature and precipitation, and waits here, and then it's allowed to go back up to the top. So the trick is this function, wait barrier. We're going to come back to that. The animals, well, they're in the same while loop. The same condition that governs when the watcher finishes also governs when the animals finish, which might be never. They're going to compute, they're going to look at the global state, and they're going to compute what their next value is. How many of us will there be now? Will we increase in population? Will we decrease? And they're waiting at the same barrier, this orange rectangle right here. Now they copy their next thing they computed into the now state, the current state, because now by passing this barrier, we know that all quantities are done using the current state. Waited a barrier. Now in here, they do nothing because the watcher thread's running. Wait at the barrier. And then everybody can go back up to the top and do it again. So all these threads are working in lockstep through this process. And they have to be. Otherwise, they get out of sync. So when I was playing with this, here's what I got. Time goes like this. And I had environmental variables, rainfall in blue, temperature in this dark red. Plants were green, animals were this red. And you can see some of the patterns here. When there's a whole lot of plants, well, then the animal population rises, but then the animals overeat the plants and the plant population falls. And so the animal population falls, which means the plants aren't being eaten enough. So the plants start to recover and so on. Okay. And this is typically what this kind of simulation gives you is some curves that are out of phase. This goes up, therefore that starts to go up, but then this goes down, therefore that starts to go down. And this is the kind of thing you do. But this is a nice way to program because each one of those functions only has to worry about itself. Yeah, you could probably put together a for loop or a while loop where you're worrying about everything at once. But this is such a nice, straightforward way to program. Each function worries about itself. Okay, now we could just put, every time we need a barrier, sure, let's just put pound pragma OMP barrier in there. And that won't work. Why? Because, well, when I think about barriers, I can think of two ways to implement them. One way would be to put some code at a particular address and then put some kind of check so that when each thread gets to that address, that's when they stop and wait for the others. I can think of another way to implement barriers where you just, each thread says wait, like we're doing here, wait barrier, calls a function. Turns out that in the OpenMP spec, this is the only one that's allowed. But that messes with our functional decomposition because these are different functions. And so if I put a pound pragma barrier right here, that's not the same place in memory as if I put pound pragma barrier here. So it turns out this doesn't work because the OpenMP spec says it's got to be this one. So we have to implement that one because that's the one we're using. And here's what we've done. And so you have access to this code. It's in the functional decomposition handout. You need to call a knit barrier at the top of your program to let it know how many things it's going to wait for. 3, plants, animals, and watcher thread. Okay, that just lets it know. Now, down here in wait barrier, which everybody calls when they want to catch up with each other, we set the lock. We check to see how many are waiting at the barrier. If it's the right number, then we go ahead and release everyone. If it's not, we're going to wait. And that's what's going on here, is it's just waiting until the correct numbers show up. So that's why this has got to be correct. Okay, if you've got 3 quantities, including the watcher, set this to 3. If you've got 4, set this to 4. If you get that wrong, then I don't know, usually it means deadlock because it's waiting for something here that will never happen. Okay, if you care, as you call this, this is the state of the variables, if you care, but this works. So anyway, this is functional decomposition, and it really simplifies this kind of programming because each function only has to worry about its quantity and how that quantity reacts to the world around it. Okay, you don't have to build in multiple quantity logic. It's just each function is separate, but they're synchronizing with these wait at the barriers.